Hi everyone, my name is Andong Li and I'm honored to be here to give a presentation about our subject paper, a recursive network with dynamic attention for Monaural speech enhancement. The authors are Andong Li, Chen Shizhen, and Chuanfan Renhua and Xiaodong Li. I will introduce the work from 4 points, namely background, proposed algorithm, experiments and analysis, and conclusion. Let's begin the first part. In real environments, speech is often contaminated by background interferences like environmental noises or reverberation. These noises will distort the performance of automatic speech recognition system and hearing assistant devices. Recently, the introduction of deep neural networks facilitated developments of the research towards speech enhancement. Many different types of networks are proposed afterwards. For example, feed-forward layers, convolutional neural networks, CNN, and recurrent neural network, RNN. Compared with feed-forward, CNN and RNN are better at speech tasks. For CNN, it can learn the local patterns of the spectrogram, and for RNN like LSTM, it can learn the sequence correlations between consecutive frames. In addition, convolutional recurrent network, CRN, is also proposed, and it has both the advantages of CNN and RNN. However, to realize good performance, loss parameters are usually required, which may limit the latency requirement. In addition, the increase of lateral depth may also cause gradient variation problem. In 2009, Banjo proposed a type of learning paradigm called progressive learning, which means that the original hard problem could be decomposed into multiple easier subproblems. So it is much easier for network to map the target. Recently, progressive learning is also applied into speech enhancements. However, for each stage, a separate network is usually used. It means that a larger network parameters are needed. So we began to wonder whether it is possible for network parameters in each stage to be shared. Based on that, we propose a new training paradigm called recursive learning. That means that the network is shared at each stage, and meanwhile, a type of module called stage recurrent neural network, dubbed SRN, is also adopted to grasp information across different stages. In addition, in this paper, we also propose a module called the dynamic attention module to assist the network training. It is based on the human behavior. People tend to generate different attention toward different noisy inputs. For example, when the environment is quite noisy, to hear someone's words, one has to pay much attention. And if the noise is not dominant, maybe less attention is needed. Let's go to the second part. I first introduced stage recurrent network and SIN. As the figure shows, it includes two parts, namely a convolution layer and a conv-GRU module. Convolution layer receives both a noisy target magnitude spectrogram and .TMS and the estimation from the last stage to obtain the encoded feature H hat L. Then conv-GRU will receive both H hat L and H L masked one to update the output feature, HL. The calculation of conv-GRU is also given, as dotted line shows. It can be noted that the expression are quite similar to the GRU we often use, except all the fully connected operations are replaced by the convolution operations. In this paper, we use a module called attention gate and .AG. It is used into a variant unit called attention unit and .AUNet. Compared with naive UNet, AUNet can automatically suppress the irrelevant regions and emphasizing the important features. The schematic diagram of AG is shown below. There are two inputs, namely P and Q. First, both inputs will pass and convolution layers with 1.1 kernel. Then the outputs will be needed. And then pass ReLU and another 1.1 convolution. And the sigmoid function is used to scale in values into 0 to 1. The output values will serve as a weighting coefficients and multiply by Q. Here, P and Q refer to the features in the one encoder layer and the corresponding layer in the decoder. This figure shows the overall architecture of the proposed approach. We can find that it consists of 2 points, two components, namely attention generator module dubbed AGM and the noise reduction module dubbed NIM. AGM is a module to formulate the dynamic attention mechanism of human, and NIM is a major network for noise reduction. As the figure shows, the network can be unfolded into multiple stages. At each stage, both AGM and NIM will receive noisy input and the estimation from last stage. Here, the connection between AGM and NIM is via a pointwise convolution and sigmoid function. For AGM, in this paper, we adopt a naive unit as a network. So we extract the outputs of different decoder layers from AGM, and after the sigmoid function, the coefficients are multiplied by the corresponding layers in the NIM encoder. In this way, the connection between AGM and NIM can be established. When different noise inputs are given, different coefficients from AGM are generated. So it can dynamically modulate the feature distribution of NIM. Figure B shows a network of NIM. We can find that it includes 4 parts, namely previously mentioned SRN, convolutional encoder, and multiple gated linear units dubbed GLU, and convolutional decoder. Previously mentioned AG is used hearing. In addition, we stack 6 GLU for better sequence modeling. Let's move to the experiment part. In this study, we used the timid corpus and 4,856 and 800 and 100 clean occurrences are selected as a training and validation and test set for signal-to-noise ratio -5 dB to 10 dB with 1 dB interval is for training, and 4 signal-to-noise ratio conditions are set for test, namely -5 dB, 0, 5, and 10 dB. For noise set, we select 130 environmental noises for training and 5 unseen types selected from noise line 2 are for test. Therefore, we create 40,000 and 4,800 noise clean pairs for level training and validation and test. In this paper, we select 4 baselines, namely SLSTM, CRN, GRN, DCN. SLSTM is static LSTM. 4 layers are set, and each have 1,040 and 1,024 units. CRN is a convolutional encoder and decoder architecture with 2 LSTM layers as a bottleneck. GRN and DCN are 2 state-of-the-art models with dilated convolutions. The parameter setup is given as follows. The window size is 20 milliseconds and with 50% overlap. 320 point FFT is used, and the TMS is the feature for both input and output. Because we use multiple stages, so we use the combined loss function, and the loss coefficient lambda L, and L is equals to 1 to Q is set to 1. It means that the same emphasis is given to each stage. The objective results respect to seen and unseen noises are shown in the 2 table. PASQ and STOI are chosen as the evaluation metrics. Here, the number of stages, Q, is set to 3 for default. One can find that compared with the baselines, the proposed method obtains consistently better performance. For example, we can say that the proposed method achieves average 0.15 and 1.03% improvements in terms of PASQ and STOI. In addition, we also noticed that CRN, GRN, and DCN all achieve better performance than LSTM. And this is maybe because LSTM may neglect the structured characteristic of the spectrogram, and therefore limited performance is obtained. We also analyze the impact of different stage number. One can find that when Q is less than 3, consistent improvements can be observed with respect to both PASQ and STY. However, we also find that when Q is set to 4 or 5, where STY is still improved, no improvement is observed for PASQ. This is maybe the optimization toward PASQ and STY is not quite consistent. And therefore, when MSE is further optimized, the situation for PASQ and STY may be slightly different. We also gave the comparisons about the number of parameters of different models as the table shows. We can find that the proposed method achieved a notice parameter burden. Let's conclude the paper. We propose a framework for loss removal with combined dynamic attention mechanism and recursive learning together. Dynamic attention is utilized as an auxiliary subnetwork which dynamically adjusts the feature distribution of the mini network. And recursive learning is utilized with SRN to refine the results stage by stage. And the experiments indicate that the proposed approach outperforms the baseline consistently and further decreasing the parameter burden. And that's all for the presentation, and thanks for your attention.